Hello my dear students, welcome to IMS GATE Academy GATE Foundation course on digital circuit subject. In this particular session, we will discuss regarding the logic gates part 3. So in the previous sessions, we have discussed regarding logic gates, 2 sessions we already covered. So those who couldn't watch those sessions, kindly watch that particular sessions in your free time. So first of all, let us see what are the topics that we have covered in the last session. So in the last session, we have discussed regarding the universal gates, that means NAND gate and NOR gate, okay, regarding the truth table, logic symbol, functionality, and the and everything we have discussed, okay. And then we have discussed regarding the special gates also, like exclusive OR gate and exclusive NOR gate, and regarding the truth table, logic symbol, and functionality, everything we have discussed, and in which particular case we will get out as 1, in which case we will get out as 0, etc. And then we have discussed regarding the NAND gates. See, NAND gates and NOR gates are called as what? Universal gates, right? So, and in one of the earlier session, we have discussed regarding the basic gates. Basic gates, we are having 3 gates: AND gate, OR gate, and NOT gate, right? So, by the combination of those basic gates, we can implement any Boolean function, right? Now, NAND gates and NOR gates, we are calling as universal gates. Universal gates. The reason is, with the help of NAND gates, we can implement any Boolean function. Similarly, with the help of NOR gates, we can implement any Boolean function, right? So, in order to prove that particular statement, what we can do, if we are able to implement the basic gates with the help of NAND gates, all the AND gate, OR gate, NOT gate. Similarly, with the help of NOR gates, if we are able to implement all the basic gates, that means we can say that with the help of NAND gates, we can implement any Boolean function. Similarly, with the help of NOR gates, we can implement any Boolean function. Yeah, good evening, Gopal. Good afternoon. Right. So, regarding the basic gates implementation with the help of NAND, with the help of NOR, that we have covered in the last class. Okay, right. So, in this particular session, we will discuss with the help of NAND gates and with the help of NOR gates, we will implement the further gates. Those are special gates, okay. I hope all of you are eagerly waiting for the session. Let us start the session regarding the implementation of XOR gate and XNOR gate with the help of NAND gates and then with the help of NOR gates. One by one, we'll see all the cases. So all of you put the heading implementation of special gates using universal gates. Yeah, good evening, Ravi. Good evening, everyone. So all of you put the heading implementation of special gates using universal gates. Right. So first let us implement exclusive OR gate by using NAND gates. Exclusive OR gate by using NAND gates. So first of all, write A XOR B expression. A XOR B is nothing but A bar B plus A B bar. A bar B plus A B bar. Okay. Now we have to implement this particular expression with the help of NAND gates, right? So just recall, whenever you are having 2 input NAND gate, say for example, if you are having AB are the inputs, then 2 input NAND gate will produce the output like AB bar. By using De Morgan's law, this one we can write as A bar plus B bar. Okay, right. Suppose in this particular expression, okay, somehow or other, if you are having the expression like this, A bar plus B bar, that we can write it as AB bar by using De Morgan's law. Okay, here I will do some manipulation, because directly if you observe this particular equation, you don't have like A bar plus B bar. Okay, so now I will do some manipulation here in such a way that in order to get A bar plus B bar, so once if you are getting expression like this, that you can generate with the help of a 2 input NAND gate. Why we are doing that manipulation, I will discuss after some time. For the time being, just focus whatever the manipulation here I will do, whether those steps is clear or not. Okay, that much you focus. Why I am doing that kind of modification, I will give the conclusion after some time. Okay. So here what is the expression is there, I am copying as it is. That is A bar B plus A into B bar. After that, I am simply adding 2 zeros. Whenever you are adding zeros, the resultant function will remain same, correct? Now, this 0 I will write it as A into A bar. This 0 I will write it as B into B bar. A bar B plus AB bar. Now, this 0 I am writing it as A into A bar plus this 0 I am writing it as B into B bar. I hope up to this point it is clear. Whatever the original function I copied as it is. After that I have added 2 zeros. Regarding 1 0 I have written as one variable normal form multiplication of complement of that variable. Similarly here another variable complement of that variable. Now here we have to observe the terms in such a that somehow or other we have to get A bar plus B bar. A bar plus B bar. That is our intention. So from the middle two terms, you can take A as common. If you take A as common, then you will get A bar plus B bar. A bar plus B bar, right? Similarly, first and last terms. From those two terms, you can take B as common. Once if you take B as common, once again you are getting A bar plus B bar. A bar plus B bar. Now you can observe A bar plus B bar you are getting. That means you can write A bar plus B bar as AB bar. AB bar. Okay, right. Now if you observe this particular expression, you are having like this entire term you can assume like X. This entire term you can assume like Y. It is like X plus Y format. X plus Y format. Like OR gate. Simple. Okay. In the last class we have discussed regarding the OR gate with the help of NAND gates. What we have done? Can you recall? If you are having X plus Y, if you want to implement by using NAND gates, what we have to do? Just recall what we have done in the last class. If you are having X plus Y, this is normal output. But whenever you are implementing with the help of NAND gate, by default you will get what? Complement version, right? So what we can do, just perform 2 times complement, you will get the same function, right? Now for the inner complement, you can use De Morgan's law. For the inner complement, apply De Morgan's law. X plus Y whole bar is nothing but X bar and Y bar, and keep external complement as it is. Keep external complement as it is, right? So the same procedure you can apply here. That's all. So here the first term you can consider like X, second term you can consider like Y. That means first term complement, second term complement, and then overall complement. That's all. Okay. A into AB bar plus B into AB bar 2 times complement. For inner complement, you can use De Morgan's law. First term complement. First term complement. So up to here, this is the first term complement. Here logical or logical AND. Now second term is what? B into AB bar. So this is the second term. So second term complement, and then keep external complement as it is. Keep external complement as it is. Okay, it's like X bar, Y bar, whole bar. So X is nothing but this entire term, and similarly Y is nothing but this entire term. After that you are getting complement and then overall complement, right? So now just look at this particular expression. Look at this particular expression. How many 2 input NAND gates we require? How many 2 input NAND gates are required for implementing this particular expression? Any guess? It is very simple. Just look at the expression and tell me how many 2 input NAND gates we require. Yes, in general, most of the students will say that 5. Okay, but whether really we require 5 or not, let us see. See, here AB bar, for this you require one 2 input NAND gate, right? After that output and then A, you are passing through one more NAND gate, second NAND gate. Now just observe, here already AB bar we got, here also you are having AB bar. That means output of a 2 input NAND gate, that NAND gate output you can use here also, right? You no need to generate this one once again with the help of one more NAND gate. But generally students will count this one, for this one also you require one more NAND gate, right? But both the expressions are same. Just observe AB bar, AB bar. That means one time if you are able to implement that one, that output you can use as input, that's all. So that means this already we have generated. Now here we require fourth NAND gate for this, third NAND gate. For this NAND gate, B and this AB bar both are the inputs, and then assume like this entire expression is like Y1, this entire expression is like Y2. So Y1, Y2 whole bar, that means fourth NAND gate. Yes, very good Ravi, very good. 4 NAND gates are sufficient. 1, 2, 3, 4. Okay. So let us draw the circuit diagram for this one. So initially if you observe both the terms, AB bar is same. So for the time being, first let us implement that one. AB are the inputs. Output of this NAND gate we will get AB bar. AB bar. Now here we require one NAND gate, here we require one NAND gate. And for these two NAND gates, one of the input is AB bar. One of the input is AB bar. That's why the output of first NAND gate I have given as the input for these two NAND gates. Now for this NAND gate, another input is A. For this NAND gate, other input is B. Okay, right. So just for easy understanding, if you want, you can, I am just labeling, this is first NAND gate, this is second one, this is third one. First NAND gate, second NAND gate, third NAND gate. Up to here we got. Now output of this one, second NAND gate, is like Y1. Output of third NAND gate is like Y2. Y1, Y2 whole bar. That means we require one more NAND gate. So for that NAND gate, we are giving these two outputs as the inputs. So finally, we are getting here, this is the fourth NAND gate. Output of this one, we are getting A XOR B. So for implementing a 2-input XOR gate, we require 4 NAND gates. We require 4 NAND gates. Okay. I hope whatever the adjustment or manipulation here I have done in order to get the expression like this. Okay. In order to get the expression like this, after getting the expression like this, okay. So that is whatever the expression here you are having, this expression is in the form of like x plus y. So we have applied 2 times complement. For inner complement, we have applied De Morgan's law. If you do like this manipulation, then we are getting 4 NAND gates are sufficient for implementing a 2-input XOR gate. Okay, right. So some of you might be having the doubt, sir, how to do this kind of manipulation in the exam. Okay, so don't worry at all. Whatever the expression you got here, for the time being, I am labeling this expression as equation number 1. Okay, in order to get this particular equation 1, I will give one more approach. Okay, once if you are getting somehow other expression like this, after this, in order to do the adjustment like this, you are very much familiar. Okay, there is no confusion at all. Now, in order to bring this particular expression into this expression, okay, so I will give one more approach. Just pay attention. So first of all, I am writing A x nor B expression. A x nor B, that is nothing but A bar B bar plus AB. A bar B bar plus AB. Now just apply dual. Just apply dual for this expression. What you will get? A bar plus B bar. A bar plus B bar into A plus B. I have considered a two input XNOR gate expression and I have applied dual. Okay. Now, what is the overall equation? What is the overall equation you are going to get? If you apply dual to the two input XNOR gate, what you will get? Regarding this, we already covered in the Boolean algebra chapter. Even in the logic gates also in the beginning we have discussed. So just recall and tell me what is the expression you are going to get here if you do further simplification. See, it is very simple. Just observe. A bar into A is nothing but what? 0. A bar into B, you are getting A bar B plus B bar into A is nothing but AB bar plus B bar into B is what? 0. Okay, so that means you are getting what? A XOR B. A XOR B. See, only for two input case, XOR gate, XNOR gate, those two are dual to each other and those two are complement to each other also. In general, whether you are having two inputs or more than two inputs, in general, XOR gate, XNOR gate, these two are complement to each other. But only for two input case, you are getting one more special feature. So XOR gate, XNOR gate, those two are dual to each other also. Okay, so that is the property that I have used here. I have considered A XNOR B expression. I have applied dual. I am getting A XOR B expression. Right? So now you are having A bar plus B bar. By using De Morgan's law, this one we can write as A bar plus B bar, we can write as AB bar. Yes or no? AB bar into A plus B. Now just multiply this term with these two. That's all. A into AB bar plus B into AB bar. Now just observe whatever the equation here I got, whatever the equation here you are having, whether both are same or not. See, regarding equation number 1, A into AB bar plus B into AB bar. Yes, we are getting the same equation. So this is one more approach, easy approach in order to get the expression like this. Okay, right, very good. So either with the help of this method or with the help of this method, okay, somehow or other if you are getting equation like this, after that you are following 2 times complement. For inner complement you are applying De Morgan's law, etc. With the help of this one you are getting 4 NAND gates. Now if you carefully observe, whatever the manipulation I might have done here, or with the help of this approach, somehow or other, whatever the equation number 1 we are getting, that is in the form of x plus y. Now if you carefully observe, even in the beginning when you have written A XOR B expression, here A bar B plus AB bar, this one you can consider like x, this one you can consider like y. X plus y, original equation itself you are having x plus y, but why I have done so much manipulation, after that I have implemented here. So all of you give a try. See, it's not that we cannot implement A XOR B with the help of this expression. No, we can implement. See, all of you just give a try. Here original equation also like x plus y format. So just apply 2 times complement. For inner complement use De Morgan's law and tell me how many NAND gates are required if you are implementing for this expression directly. Now all of you give a try, so that you will come to know that why I have done this much manipulation. Yes, all of you give a try. For the direct expression also we can implement with the help of NAND gates, but how many NAND gates we require? Yeah, Kundan, you can cross check once. Wow, congrats Kundan. Yeah, Ravi, you are telling 4. Okay, we'll cross check. So what I told is directly you can consider this expression A XOR B. A XOR B is A bar B plus AB bar. A bar B plus AB bar. Now this expression is like X plus Y format. X plus Y format. Yes, Kundan, I remember. Yeah, congrats. X plus Y. Okay, so just perform 2 times complement. Just perform 2 times complement. You will get the same function, right? So for inner complement, use De Morgan's law. First term complement and second term complement and keep external complement as it is. First term is A bar B. Second term is A into B bar. I am repeating once again. I kept external complement as it is. For inner complement, I have applied De Morgan's law. First term complement, second term complement. Okay. So now just observe. For implementing A bar, we require one NAND gate. Yes, very good, Kundan. Very good. If you are having 2 input NAND gate, if both the inputs tied together, then that particular 2 input NAND gate will behave as NOT gate, right? So here for generating A bar, we require one NAND gate. Similarly, for generating B bar, we require one NAND gate. Okay. And then here for getting A bar into B whole bar, third NAND gate. Similarly, here fourth NAND gate. And then assume this is like Y1, this is like Y2, Y1, Y2 whole bar. That is fifth NAND gate. Okay. So if you want directly the A XOR B expression, we can implement with the help of 2 input NAND gates, but we require 5 NAND gates. If you directly implement like this, then we require 5 NAND gates. Why we are getting fifth NAND gate? It is very simple. Just observe previous expression. Here in this term AB bar is there, in this term also AB bar is there. Same term was present. That's why, that is the reason somehow or other, if you are able to implement AB bar one time, okay, because of that, what is happening? We are reducing one NAND gate. But in this particular expression, for A bar we require one NAND gate, for B bar we require one NAND gate. So that means we require one more additional gate, right? So that is the reason here we require one more extra gate. Whereas if you do the manipulation like this or like this, okay, you require only 4 NAND gates, right? In the gate exam, always they will ask regarding the logic gates, always they will ask minimum number of gates, okay? If they ask minimum number of gates, obviously 4 is the correct answer. Of course, we can implement the same A XOR B with the help of 5 NAND gates, okay? Nowadays, you are having MSQ type of question. So if they want, they can frame the question like this also. So they can frame in the options like this regarding A XOR B. We can implement A XOR B with the help of 4 NAND gates. And another option is like we can implement A XOR B with the help of 5 NAND gates. So both the options you have to choose because both options are correct. Yes, very good, Ravi. Very good. Okay, I hope all of you got the clarity regarding the A XOR B or 2 input XOR gate implementation by using 2 input NAND gates. Okay, right. Now whatever the circuit here we are having, in this entire circuit diagram, we are having NAND gates, right? Yes, very good. Now, instead of NAND gates, you can use NOR gates. Okay, instead of NAND gates, just keep NOR gates. Okay, then the overall circuit will become what? Just identify. Wherever NAND gates are there, just replace NAND gates with NOR gates. then the overall circuit will become what? So if you want, I will give the hint. What is the relation between NAND gate and NOR gate? How those two are related to each other? What is the relation between NAND gate and NOR gate? If you are able to identify that particular hint, then you can easily answer my previous question. See, NAND gate and NOR gate are what? Dual to each other. Dual to each other. Just like AND gate, OR gate are dual to each other. NAND gate, NOR gate are dual to each other, right? So in place of NAND gates, if you are keeping NOR gates, then the overall circuit will become dual of this particular expression, right? A XOR B dual is what? A XOR B, A XOR B. So that means if you want to implement XOR gate with the help of NOR gates, the same circuit diagram you can consider. Instead of NAND, just consider NOR gates. That's all. Okay. So that means with the help of 4 NOR gates, you will get A XOR B. A XOR B. So just put the heading XOR gate using NOR gates. XOR gate using NOR gates. Okay. So just make a note. In the above circuit, that means whatever the circuit we have discussed in the last slide, in the above circuit, by replacing NAND gates with NOR gates, we will get XNOR gate. That means for implementing XNOR gate, that is for implementing a 2-input XNOR gate, we require for implementing a 2-input XNOR gate, we require 4 2-input NOR gates. We require 4 2-input NOR gates. Okay. So for implementing XOR gate, we require 4 2-input NAND gates. Similarly, for implementing a 2-input XNOR gate, we require 4 2-input NOR gates. Now with this understanding, so just observe this particular circuit diagram. So far we got XOR. Now, up to now we are having 4 NAND gates. Okay. Now I want to use NAND gates only. In order to get XNOR, what we can do? Up to this circuit diagram, whatever the 4 NAND gates we are having, 3 stages together, this overall circuit diagram I will consider. The output we are getting A XOR B. But now our requirement is I want to get A XOR B. So what we can do? Output of this XOR, I have to pass through which logic gate so that I can get A XOR B. Yes. What is the relation between A XOR B and A XOR B? Those two are complement each other, right? So here my requirement is I want to implement with the help of NAND gates, right? So I already implemented A XOR B with the help of 4 NAND gates. Now the output of this one, if you pass through NAND based inverter, then A XOR B complement is nothing but A XOR B, A XOR B, right? So next one, put the heading XNOR gate using NAND gates. XNOR gate using NAND gates. Whatever the circuit diagram we have discussed regarding XOR gate using 4 NAND gates, the entire circuit diagram, instead of drawing the circuit diagram, just keep as the block diagram. Whatever the circuit diagram we have discussed, just keep as a single box. Okay, right. 2 input XOR gate, XOR gate using NAND gates, 2 input XOR gate using 4 NAND gates. We have used 4 NAND gates, right? So here AB are the inputs, output you will get A XOR B, This circuit diagram we have seen, so just I have represented as a single block. Okay, right. Now this A XOR B, we are passing through a NAND based inverter. NAND based inverter means if you connect both the inputs tied together, then 2 input NAND gate will behave as NOT gate, right? So here you will get output as complement of input, that means A XOR B complement is nothing but A XOR B, So here I have used 4 NAND gates, now here I am using 5th NAND gate. So that means for implementing a 2 input XNOR gate, we require 5 NAND gates, okay, right. Similarly here we have already generated a 2 input XNOR gate, by using 4 2 input NOR gates. By using 4 2 input NOR gates, we got a 2 input XNOR gate. Now I want to get XOR gate. What we can do? I want to get XOR gate. Whatever the circuit diagram here you are having, consider the same circuit diagram, but after that, which logic gate we have to use so that I can get XOR? The overall circuit will become XOR. Any guess? Yes, just apply the same logic. See, here you are having one circuit diagram. That circuit diagram is producing output as what? XNOR. But my requirement is what? I want to get XOR. That means XNOR output, if you pass through NOR based inverter, then XNOR complement is nothing but XOR. That's all. Okay, next one, put the heading XOR gate using NOR gates. XOR gate using NOR gates. So earlier we have implemented 2 input XNOR gate, 2 input XNOR gate using 4 NOR gates. 2 input XNOR gate using 4 NOR gates we have implemented, right? So that one I have represented as single block. Here inputs are AB, output you are going to get A XNOR B. Now this output we are passing through a NOR based inverter. Okay, then this NOR based inverter, okay, it is very simple. You are having 2 input NOR gate, both the inputs I have tied together, then this 2 input NOR gate will behave as simply NOT gate or inverter. So output you will get complement of input, that means A XNOR B complement, which is nothing but A XOR B, A XOR B. Here we have used 4 NOR gates, and then here I am using the 5th NOR gate. So for implementing a 2 input XOR gate, we require 5 NOR gates, 5 NOR gates. Okay, right. For implementing a 2 input XOR gate, we require 5 NOR gates. Okay, simple. You can easily, okay, I am just giving the recall regarding the final conclusion points. Regarding 2 input XOR gate, see here all the logic gates that we have implemented for 2 input only, and for implementing 2 input logic gates we have used 2 input NAND gate or NOR gate. Okay, right. So here all the logic gates that we have discussed, all those logic gates are having 2 inputs. Okay, okay, that you can keep as a note. Now for implementing XOR gate we require 4. For implementing XOR gate we require 4 NAND gates. Now in place of NAND gates, if you keep NOR gates, okay, NAND gate dual is NOR, so that's why the overall circuit will become dual of this one. Dual of XOR is nothing but what? XNOR. That means for implementing XNOR we require 4 NOR gates. Okay, now up to here we got XOR. Now this one, if you are passing through NAND based inverter, then complement of XOR is nothing but XNOR. That means for implementing XNOR gate we require 5 NAND gates. Okay, similarly for the last case you will get 5 NOR gates. 5 NOR gates for getting A XOR B. I hope it is clear for everyone. Okay, now let us make the tabular form regarding the minimum number of NAND gates or NOR gates required. Okay, so before this, okay, right. So far we have discussed in the last class, we have discussed with the help of NAND, with the help of NOR, we have discussed how to implement the basic gates like AND gate, OR gate, NOT gate, and in this particular session we have discussed regarding XOR gate, XNOR gate. Now whatever so far we have discussed, okay, let us make in the tabular form. So the first column is logic gate. Okay, first column you can put the heading logic gate. Okay, we have discussed regarding NOT gate implementation, AND gate implementation, OR gate implementation, and then XOR gate, and then XNOR gate. Up to here we have discussed. Okay, first let us focus up to here. After that we'll continue further, just for understanding purpose. Okay, we'll discuss further. Right. So here minimum number of NAND gates required, minimum number of NOR gates required. What is the condition here? If only the normal inputs are available. If only normal inputs are available. If only normal inputs are available, then we'll write the minimum number of NAND gates required, minimum number of NOR gates required. Whatever we have discussed so far in the last session and this session, so far whatever we have discussed, that is the case only when the normal inputs are available. In general, in the question, sometimes they will specify regarding the inputs in which form they are available. If they don't specify regarding the inputs, by default, suppose if you are having XOR gate, you will apply AB are the inputs. That means both the inputs are normal form, right? So whenever they don't specify regarding the inputs in which form they are available, by default you can consider those inputs are normal form, okay? But sometime in the question they will specify that the inputs are available both normal and complement. Okay, if they specify like that, then according to the context the answer can vary. Okay, so you have to read the question carefully, especially while you are attempting the questions regarding the logic gates, because the question is what? Regarding the minimum number of NAND or minimum number of NOR gates required, but based on the context the answer will vary, right? So that's why you have to read the question carefully and you have to attempt the question accordingly. Otherwise your answer, you are attempting with respect to one context, but according to the question point of view, if there is a different context, then answer can vary, right? So that's why you have to pay attention, but especially while you are attempting the question based upon this particular concept. Of course, for any question when you are attempting in the GATE exam, you have to read the question carefully, but especially in the digital circuit subject, whenever the questions regarding the inputs, okay, so for some concepts there will be main keyword. If you are missing that particular main keyword, okay, then what will happen? You may be correct at whatever the answer you are providing, but according to the context, if that is not correct, then even though you are good at the concept, but your answer will be wrong, right? So that's why try to avoid such kind of silly mistakes in the GATE exam. Okay, don't be overconfident, especially when you know the concept very well. Okay, right. Okay, so first of all, let us fill this tabular form. After that, I will fill the tabular form here. Okay, right. So first of all, NOT gate. NOT gate output is what? A bar. NOT gate output is A bar. Okay, so here we require one NAND gate, and similarly for NOR gate also we require one. That's all. See, both the inputs if you tie together, then 2 input NAND gate will behave as NOT gate. Similarly for NOR gate also. Okay, NOR based inverter, NAND based inverter. Next, AND gate. AND gate means AB will get, but if you are using NAND, by default you will get complement version, but we require normal, so that's why we can apply once again complement. So that means we require 2. We require 2 NAND gates. Okay, I will come back here regarding this one. Regarding OR gate will focus. Regarding OR gate, A plus B. Regarding OR gate, by using NOR. When you are using NOR, by default you will get complement. So once again, if you apply complement, you will get normal function. So that means we require 2 NOR gates. Okay, right. Fine. Then if you want to implement AND gate by using NOR. If you want to implement AND gate by using NOR, what you can do? Same procedure. You have to apply 2 times complement, but your requirement is you want to implement by using NOR, right? So that's why you can apply De Morgan's law for inner complement. So AB bar is nothing but A bar plus B bar, and keep external complement as it is. External complement as it is. Now in this case, how many required? 1, 2, 3. We require 3 2 input NOR gates, right? Now similarly regarding OR gate, OR gate by using NAND gates. So here you have to apply De Morgan's law. You have to use De Morgan's law. You will get A bar into B bar whole bar. So here also we require 3. See, I hope it is clear for everyone. See, I am recalling once again regarding NAND gate with the in order to implement NOT gate, it is very simple. Similarly for NOR gate, NOR based inverter also simple. And regarding AND gate, by default you are getting complement version, but you want normal. So what you can do? Output of NAND gate you can pass through NOT gate, NAND based NOT gate. So that's why you will get AND gate. So that's why we require 2. Similarly, the case for OR gate. OR gate by using NOR gates. First of all, you are getting NOR gate output, and then that output you are passing through NOR based inverter. So we require 2 NOR gates. Now, in this case and in this case also, we are applying 2 times complement, but only the difference here I haven't applied De Morgan's law for inner complement, but here I have applied. The reason is very simple. Based on the context, whether you have to apply the De Morgan's law or not, which logic gate you are using, based upon that one. See, if you are using NAND gate, by default if you observe under the complement you are having what? Logical AND. So that expression you can implement with the help of NAND. So whenever you can implement with the help of NAND, that time you no need to apply De Morgan's law. But here you want to implement with the help of NOR gate. NOR gate, that means under the complement you should have the function like x plus y format. That is the reason here I have applied De Morgan's law. Okay. Similarly, here also if you observe with the help of NOR gate, directly you are getting this particular expression a plus b whole bar. So no need of De Morgan's law. But here you are having a plus b whole bar, but I want to implement with the help of NAND. That means under the complement you should have the function like logical AND among 2 variables, right? So that is not there here. In order to bring to that particular function, we are using De Morgan's law. That's all. Okay. So if you want to answer any question regarding the logic gates, especially when they ask how many 2 input NAND gates required or how many 2 input NOR gates required for implementing any logic gate or for implementing any logic function. Okay, it is very simple. If you are able to remember the basic gates how we have implemented, if you recall this particular basic gates implementation with the help of NAND and NOR, you can answer any question correctly you can do. Okay, and you can remember this logic. And if you want to represent in another way in terms of Boolean functions, okay, whenever you are having the original Boolean function, after doing the simplification, you will get what? You will get either SOP form or POS form. Okay, so regarding this also you can easily understand, and I will give the conclusion point or brief summary with respect to SOP POS also in some time. Okay, right. So either with the help of that logic or with the help of this logic, you can answer any question regarding the minimum number of NAND gates or minimum number of NOR gates required. Okay, but only one important point you have to take care is according to the context, according to the sentence that they have mentioned in the question regarding the inputs. Okay, if they don't mention anything regarding the inputs in the question, that means by default the inputs are available in normal. Okay, but sometime in the question if they specify that the inputs are available in both normal and complement, then that time you have to take extra care because your answer may vary, right? If answer is same in this case, that case, then no problem, definitely you will get the correct answer. Okay, but according to the context, if answer vary, then you have to attempt that question accordingly, right? So according to the given context you have to attempt. Okay, that much care if you are able to take, no matter whatever may the level of the question in the GATE exam, all of you can attempt correctly, right? Okay, so far we have discussed regarding the basic gates, and then regarding XOR gate just now we have discussed. Okay, by using NAND gates we require 4, and here in this entire circuit, if you replace NAND with NOR, we are getting XNOR gate. So that means for implementing XNOR, we require 4 NOR gates. Okay. Yes, Ravi. Okay. Regarding that, I will discuss in some time. Okay. So up to here we got 4. Okay. Now for other case we got 5. For other case we got 5. Okay. See, in the exam, here regarding XOR gate, XNOR gate, whatever the 4 circuits we have discussed, okay, we got the final answer either 4 or 5. Okay. So in order to, here for understanding purpose I have discussed completely, but if you are getting direct question regarding XOR gate or XNOR gate with respect to NAND or NOR, if only normal inputs are available, instead of solving the question like that, it is very simple. If you are able to remember one small trick, with the help of the trick you can answer any question related to this concept, like 4 possible cases are there, right? So for any of these 4 questions you can easily attempt. It is very simple. It is very simple. Just remember this one logic. Here XNOR gate is there, XNOR gate, and here NOR is there. Okay, in both the terms NOR is same. In both the terms NOR is same, right? So for that one case you remember answer is 4. Here NOR is there, here also NOR is there. For this case just remember answer is 4. Okay, now you are having XNOR gate with the help of NOR gates. Okay, in place of NOR gates, if you consider NAND, NOR gate dual is what? NAND gate. Now the overall circuit will become what? Dual. So XNOR dual is what? XOR. XNOR dual is XOR. So that means we require 4 NAND gates. 4 NAND gates. Once if you are getting 4 for one case, obviously for other case is what? 5. That's all. Okay. So in this way, remember for one logic, with the help of this one logic, you can answer any question. Here 4 possibilities. Okay, right. So up to here we have discussed. Now let us fill the tabular form here if both normal and complemented inputs are available. If both normal and complemented inputs are available. If both normal and complement inputs are available, then in that case, what is the minimum number of NAND gates required? What is the minimum number of NOR gates required? That is the question. Okay, right. So here in the question they have mentioned that inputs are available in both normal form and complement form. So that means since they have mentioned already complemented form available, whenever you are getting any complement version like this, okay, you don't need to once again generate because that is already available. Just like AB are available in general, in the same way A bar is also available, B bar also available. That time you don't need to generate that particular expression with the help of any logic gate. Okay, right. So here for NOT gate, output is what? A bar. And here read the question, inputs are available both normal and complement. That means now tell me, what is the minimum number of NAND gates required? What is the minimum number of NOR gates required for implementing NOT gate? If you are able to answer this question, that means you can answer any question regarding this logic gates correctly. Ravi, just read the question carefully. Here I have mentioned that the inputs are available both normal and complemented. That means here A bar already available at the input side. Okay, that means we don't require any logic gate at all. We don't require any logic gate, 0. See, in general, A, B inputs are available, normal form. Okay, that regarding that case, we already filled the tabular form here. Okay, but here they have mentioned the inputs are available in the normal form and the inputs are available in complement form, right? So whenever you require complement version, since they have mentioned that complement version is available, you no need of any logic gate. Okay, that's why I have told based on the context the answer will vary. Okay, right. Now with that understanding, now tell me regarding here for AND gate. For AND gate, what is the minimum number of NAND gates required? What is the minimum number of NOR gates required? All of you give a try. Don't hesitate even if you are getting any wrong answer, because you are all learning, right? If you are doing any mistake, That means from the mistake, you are having the great opportunity to learn, right? If you are not doing any mistake, that means you are not learning anything new, right? So that's why I always tell the students that do as many new mistakes as possible, but don't repeat the same mistake. Whatever earlier you have done, don't repeat that mistake, because if you are repeating the same mistake, that means you are not progressing, right? But if you are doing different mistakes, that means you are learning new from each and every new mistake, okay? So that you are becoming more strong on the basics, okay? Never get hesitant that whenever you are doing any mistake while solving any question, but don't do any mistake in the real GATE exam, because by that time, whatever the mistakes you are supposed to do, you have done n number of mistakes. Now there won't be any further mistake in the real GATE exam, okay? Right. Yes, very good, Ravi, very good. So here for AND gate, earlier we have written AB bar whole bar, right? So here anyway there is no change regarding in terms of NAND gate 2 only. But whereas for NOR gate, by using NOR gates, here if you observe A bar plus B bar whole bar, A bar is already available, B bar also available. So that means we require only one external NAND gate, NOR gate. So A bar, B bar, we will pass through one NOR gate. So that's why here 1. Right, very good. So with the same understanding, you can easily answer here also regarding OR gate. Yes, very good, very good. So regarding OR gate, okay, first of all, if you consider with the help of NOR, obviously we require 2. Okay, and if you want to implement with the help of NAND, here A bar is available, B bar is available. So these two outputs you are passing through a NAND gate, that's all. So that means 1 and 2, right? Now regarding XOR gate, so let us give a try regarding XOR gate with the help of NAND. Already we have discussed, just you can look at the expression. But earlier we have discussed for normal case, that means if only normal inputs are available. Okay, this is the proof we have already discussed. Now just look at this final expression, and according to the second context, that means if both normal and complement inputs are available, in that case how many NAND gates are required? Here we already got the A XOR B expression. Okay, this expression you can look at, and if when both normal and complement inputs are available, in that case how many NAND gates are required? Yes, very good Ravi, very good. See, here A bar is already available, B bar is also available. That means we no need to implement with the help of any logic gate. Okay, just earlier we got 5, but now we are minimizing what? 2. 2 logic gates are not required. That means 5 minus 2 is what? 3. Or you can observe from here also. 1, 2, 3. That's all. 3 NAND gates are sufficient. 3 NAND gates are sufficient for implementing a 2-input XOR gate by using NAND gates when both normal and complement inputs are available. Okay, right. Now let us consider same A XOR B only. So first of all, I am expanding the expression A bar B plus AB bar. A bar B plus AB bar. Okay, so now if you observe this particular expression, is in which form? Is it SOP form or POS? Is it sum of products or product of sum? See, it is very simple. Here you are having product term, here also product term. These two are what? Sum together. Yes, very good, Ravi, very good. It is SOP form. It is SOP form. Okay, you are having the original function SOP form. Okay, right. So whenever you are having the function SOP form, okay, whenever you are having the original function SOP form, you can apply 2 times complement for that particular expression. Okay, for that particular expression you can apply 2 times complement, and for inner complement you can use De Morgan's law, so that first term complement, second term complement, and keep external complement as it is. Okay, so in this way you can implement. So regarding that, we already discussed with the help of NAND gates. Okay, so original function you are having, we have applied 2 times complement. For inner complement we have used De Morgan's law, we got like this. So if you, whenever you are having the original function SOP form, with the help of NAND gates, we can easily implement. With the help of NAND gates we can easily implement. Okay, this is one approach. In general, with the help of Boolean function, after doing simplification, if you are getting SOP form, this is the approach. And now you can just recall with respect to the basic gates. Okay, so this entire expression, if you are assuming like X, and similarly the second term, if you are assuming like Y. Now this particular expression belongs to which logic gate? It is OR gate. Yes or no? It is OR gate. It is OR gate. So if you are having OR gate, form, then what you will do? You will apply 2 times complement, and for inner complement you can apply De Morgan's law. That's all. So that's why I have told, either if you remember the basic gates, how we have implemented with the help of NAND or NOR, or even with the help of this SOP POS, with the help of this discussion also, you can easily correlate. That's all. Correct. Yeah, 2 times complement. Okay, so you can visualize a function like SOP form, or you can visualize like X plus Y form. Okay, whenever you are having like that, it is very simple. You will apply 2 times complement, and for inner complement you can use De Morgan's law, so that you are getting each and every term complement. After that, with the help of NAND gates, you can easily implement. Okay, right. Now this A XOR B, if we want to implement by using NOR gates, okay, by using NOR gates, that time you should have the function, instead of SOP you should have the function POS, so that we can easily implement with the help of NOR gates. Okay, how it is, let us see. So the same A XOR B I am considering, same A XOR B expression. Here I am having A bar B plus AB bar. Okay, so but this function is in SOP, but I want to bring this function to POS. Okay, regarding that, we can use transposition law. Transposition law is very simple. Just consider like one iteration. Suppose if you are adding these two, A bar plus A, what you are getting? 1, right? So that combination you can avoid. Then you can consider other combination. Whichever combination you are not getting resultant value 1, that particular combination you can just perform addition. That's all. A bar plus A you are getting 1, that combination we are avoiding. Then we are getting A bar plus B bar, Then here whatever the other set of variables are there, just perform the logical OR, A plus B. That's all. So just carefully observe whether this equation and this equation both are same or not. Let us verify. A bar into A, 0. A bar into B, yes, we are getting this term, first term. Then B bar into A, we can write as AB bar, yes, we are getting second term. B bar into B is 0. That's all. Okay, whenever you are having the terms like this, by using transposition law, we can bring the function SOP form into POS form. Now you can observe, you are having some term, here some term. These two are product together. That means POS form. POS form. Okay. So once if you are getting like this, after that same procedure, 2 times complement. 2 times complement, same function. For inner complement you can use De Morgan's law. First term complement, here logical and here logical are. Second term complement and keep external complement as it is. Here first term is A bar plus B bar. Second term is A plus B. A plus B, that's all. Okay. You can visualize like this. Now this is the sum term, this is sum term, these two are product together, POS form. Or if you want, you can assume this entire first term is like X. Okay, first term is like X and second term is like Y. Now this belongs to AND gate, that's all. 2 input AND gate, right? So for 2 input AND gate, what we have done? We have applied 2 times complement. Our requirement is with the help of NOR gates. So just apply De Morgan's law here. X bar plus Y bar whole bar, that's all. Okay. So it is very simple. That is the reason I have told, either you can remember the basic gates implementation or you can visualize like this, that's all. Whenever you are having SOP form, it is easy to implement by using NAND gates. Similarly, whenever you are having POS form, okay, it is easy to implement by using NOR gates. Now tell me, now just look at this particular expression. When both normal and complement inputs are available, then how many 2 input NOR gates are required for implement this particular expression? Yes, very good, 3 only. A bar, B bar already available, so we require 1, 2, 3, that's all. We require 3 NOR gates. So regarding XOR gate, by using NOR gates, we require 3 only. So regarding XOR gate, with the help of NAND, with the help of NOR, we have discussed. Okay. Similarly, you can give a try regarding XNOR gate. A XNOR B. With the help of NAND, first of all give a try and then with the help of NOR. A XNOR B equal to A bar B bar plus AB. A bar B bar plus AB. All of you give a try. With the help of NAND gates, how many we required, and then with the help of NOR gates, how many we required. Yeah, Ravi, you are getting 4. Okay, we'll see. So this particular function is in SOP form. So you can implement by using NAND gates easily, right? So I am considering the function as it is. Apply 2 times complement. For inner complement, you can use De Morgan's law. First term complement, second term complement, here A bar B bar, and then keep external complement as it is. A bar B bar and then AB. Now you can cross check. I hope all of you will get the correct answer. Earlier you might have got wrong, but now you look at this particular expression, you will come the correct answer. Yes, very good. 3 only. 1, 2, 3. That's all. We require 3 NAND gates. We require 3 NAND gates. And similarly, let us give a try with the help of NOR gates, how many we require. So if you want to implement by using NOR gate, you have to bring the function SOP into POS. So I am writing the expression once again as it is. A bar B bar plus AB. Now once again use the transposition law. A bar plus A, if you consider you are getting 1, so avoid that combination. Then consider the other combination, that is A bar plus B, and whatever the remaining available you can consider. That is A plus B bar. Now you can look at this expression. It is Sum term, these two are product together, it is POS form, POS. Now, once if you are getting POS, same procedure, that's all. It is very simple. Whenever the question is regarding NAND, try to arrange the given function to SOP. If already SOP available, directly you can proceed. Okay. Similarly, if the question is regarding NOR gate, try to arrange the function to POS. If it is not available initially, then try to arrange the function to POS. Once if you are getting POS, after that it is simple procedure. Two times complement. For inner complement, you can use De Morgan's law. First term complement plus second term complement and keep external complement as it is. Okay. Now, if you look at this expression, how many 2 input NOR gates we required? When both normal and complement inputs are available. Obviously 3, right? Very good. 1, 2, 3. 3 NOR gates. So what is your conclusion point? Regarding XOR gate, regarding XNOR gate, for 2 input gates, for 2 input XOR gate, 2 input XNOR gate, if both normal and complement inputs are available, in all the cases answer is same, 3 only. In all the 4 cases, 3 only. Here understanding purpose we have solved, but if you are getting any question regarding this one, XOR gate, XNOR gate, okay, with the help of NAND or NOR, when both normal and complement inputs are available, answer is 3. You are getting different answers, like suppose in one case if you are getting 4, other case 5, in one case 4, other case 5, that possibility is there only when normal inputs are available. But if both normal and complement inputs are available, in any case, regarding XOR gate, XNOR gate, same answer. Answer is 3. Okay, I hope up to here it is clear for everyone. Okay, right. Let us proceed just for understanding purpose. Whatever the NAND gate we have considered, whatever NOR gate we have considered. Okay, let us proceed. But up to here it is more than sufficient for gate exam point of view. Just for practice, I am considering these 2 gates also once again. NAND gate, NOR gate. Obviously, NAND gate implementation by using NAND, so 1 is sufficient. NOR gate implementation by using NOR, 1 is sufficient, right? So here NAND gate means AB bar, and here NOR gate means A plus B whole bar. NOR gate means A plus B whole bar. Okay, right. So whether the question, whether only normal inputs are available or both normal and complement inputs are available. So here answer is 1, here also answer is 1 regarding NAND gate, because ultimately you are using NAND gate only, your requirement is by using NAND gates only. By using NAND gates, you are producing NAND gate output, 1 only, right? Similarly, by using NOR gates, you want to produce NOR gate. So obviously here and here 1 only. Okay, up to there won't be any difference. Now all of you give a try. For implementing a 2 input NAND gate, how many NOR gates are required? And for implementing a NOR gate, how many NAND gates are required? For first case, if only normal inputs are available, all of you give a try. Two NOR gates for NAND gate. Okay, we'll see whether it is correct or not. See, NOR gate means you have to get something like this. Under the complement, you should have like X plus Y format. But here you are having what? XY format. Okay, so what you can do, this one first of all you can expand. AB bar is nothing but A bar plus B bar. Now you are getting like X plus Y. It is like OR gate form, right? AB bar is nothing but A bar plus B bar. This is like X plus Y or OR gate. Okay. Now what is your requirement? NOR gate. So regarding that one, we already discussed. Once if you are getting OR gate, after that, if you are using NOR gate, that means you have to use 2 times complement. That's all. 2 times complement. Now, how many NOR gates we require? How many NOR gates we require? No, not 3. 4. 4 we require. See, 1, 2, 3, 4. 4 NOR gates, because only normal inputs are available, right? Only normal inputs are available. 4. Now, similarly, with this understanding, give a try. For implementation of NOR gate, how many NAND gates are required? Yes, very good, very good. You will get the same answer. A plus B whole bar, A plus B whole bar. You want to implement this one. That means A plus B whole bar is nothing but A bar B bar. Now you are getting like AND gate. You are getting like AND gate. Now you have to implement with the help of NAND. So you have to apply 2 times complement. That's all. So 1, 2, 3, 4. Here also 4 only. 4. Okay, right. So in both the cases 4 only. 4 only. Now in this context, if both normal and complement inputs are available, in that case, what is the answer? Let us see. See, first of all, let us see with respect to NAND gate. Here A bar, B bar already available. So you no need of 2 logic gates. That means only 2 are sufficient. Only 2 are sufficient. And similarly here A bar, B bar already available. So that means only 2 are sufficient. Like that. Just for practice, I have added these 2 gates also. Okay, in general, up to XNOR gate, whatever we have discussed, that is more than sufficient for gate exam. Just for understanding purpose, if you are getting different expression, okay, how to identify how many NAND gates are required. So for that case, I have just added NAND gate and NOR gate here. Okay, right. So I hope all of you got the clarity regarding the minimum number of NAND gates required, minimum number of NOR gates required, etc. for implementing any logic gate or logic function. Okay. So regarding logic function, up to here what I have mentioned, if you are having SOP, you can easily implement with the help of NAND. Similarly, if you are having POS, with the help of NOR. Okay, right. So since Ravi asked that if you are having complement version, then how to implement? It is very simple. Say for example, this particular function is in SOP, right? So that function only, if you are having complement, okay, whatever the function you got here, if that function is complement form, then what? It is very simple. Already you have implemented with the help the SOP form function by using NAND gates, correct? So after that, what you can do? So up to there you already got. See, when you are having complement of any function, okay, under the function, if you are having SOP form, first of all, you try to implement SOP form by using NAND gates. After that, what you require? You require complement. That means one more stage you can use NAND gate, but that NAND gate behave as NOT gate. That's all. NAND based inverter you can use. Similarly, say for example, after doing simplification of any Boolean function, you got POS form, but you are having on top of that complement, suppose. Okay. So first of all, you can construct POS form function that you can implement with the help of NOR gates. Okay. Whatever circuit you got, after that you just want complement. So after this circuit, just add one more NOR gate, but that NOR gate should behave as NOT gate. That's all. Okay, because here our requirement is whatever the circuit diagram we are considering, in the entire circuit diagram, you should have either NAND gates or you should have NOR gates. That is the reason we are using NAND based inverter or NOR based inverter at last stage. That's all. Okay, I hope it is clear for everyone. And here, whatever the logic gates so far we have discussed, all the logic gates are except for NOT gate, remaining all the logic gates are for 2 input only. In general, you will get the questions related to 2 input by using 2 input NAND gates or by using 2 input NOR gates only. But if they want to make the question little bit complex, they can ask for 3 input XNOR gate or 3 input XOR gate, etc. That time what you can do, whatever the expression is there regarding suppose 3 input XOR gate. Okay, so first of all you can generate 2 input XOR gate, and then that output you can pass through another 2 input XOR gate, like that. Okay, in that way you can implement the higher order or for when you're having more number of inputs, etc. But in general they won't increase more than 3. Okay, at max they can focus up to 3, because if more than 3, then definitely it will take more time, right? So that's why they won't focus. Mostly they will focus regarding 2 input logic gates only. Okay, right. So with this we have covered. So far we have started from the introduction to digital, and then we have started the number systems. There we have discussed various number system conversions, and then how to find the base or radix, and then we have discussed data representation. Okay, after that we have discussed binary codes also, and then Boolean algebra chapter we have discussed regarding with basic rules and laws of Boolean algebra. With the help of that we have done simplification of various Boolean functions, and then we have discussed min terms, max terms, and regarding that particular representation and properties we have discussed. Okay, and then whenever you are having the truth table, how to write the output expression. Okay, we can represent in 4 forms, right? All the 4 forms are equivalent for the same output variable. Okay, you can represent either in sigma m form. After doing simplification you will get SOP. Okay, or you can represent pi capital M. After doing simplification you will get POS. Representation wise those 2 functions look like different, but if you do further simplification both are like equivalent only, because ultimately you are representing for the same output variable. But in general students will get confused that both are different. Okay, but don't get confused. And then we have discussed with the help of K-maps how to do the simplification, and we have discussed regarding self-dual also. Okay, right. And then regarding logic gates we have discussed basic gates, universal gates, special gates, and then we have discussed the implementation of basic gates and then special gates with the help of NAND and NOR. And we have done very good, and we have covered in these entire sessions. Okay, we have discussed the basic concepts very well, and not only that, based on the possibility we have discussed variety of gate questions related to these concepts, and while solving those questions I have discussed both conventional approach and shortcut approach. Those who couldn't watch the earlier sessions, kindly visit our YouTube channel, IMS GATE Academy YouTube channel, and go to the playlist and see the digital circuits. Okay, so you can watch all those previous sessions if you couldn't watch in live or anytime earlier. So kindly watch those sessions in your free time, and kindly share this playlist with all of your friends so that anyone can benefit. Okay, if the student is from EC, electrical, instrumentation, computer science, this subject is a basic subject and scoring subject, and it is very much helpful for everyone. So kindly please share this playlist or these video links with all of your friends. So far we have covered regarding the basic concepts for all the branches, especially for CS branch. This is the last session, but of course for EC, electrical and instrumentation in the next week I will come on live. Okay, and here I will discuss only the basic concepts, because for EC, electrical, IN you will be having one more extra chapter like data converters. Okay, so regarding data converters, the basic concepts like with the help of KCL, KVL or voltage division rule or current division rule or op-amp related configurations, inverting mode or non-inverting mode, etc. I will cover in this particular session. This session is on Saturday, 3rd June, that is on next week. Okay, right. And then the last session, that is on CMOS logic. This particular chapter will be there only for 2 branches, EC and instrumentation, and here also I will discuss the basic concepts. In this particular last 3 sessions we have covered the logic gates, right? All those logic gates we can implement with the help of CMOS logic. That means we will use 2 types of transistors, NMOS and PMOS. Those 2 transistors functionalities complement each other. That is the reason here C stands for complementary MOS. Okay, we will discuss the basic gates and whatever the possible circuits also based on the possibility we will cover in this particular session. That session will be on coming Sunday, that is on 4th June. Okay, right. So those who are from EC, electrical, IN, so you can attend the next session, that is on 3rd Saturday June, and those who are from EC, IN can attend this last session also. Okay, so for electrical branch the syllabus is up to this chapter, whereas for ECIN up to last chapter. So I hope all of you got lot of information, and very much whatever the models we have covered in these sessions are very much helpful for all of you. Okay, so thank you everyone for attending these live sessions. Thanks a lot. So for the time being, I will stop here. Thank you everyone.